Hello, my name is Monique Dali. I conducted my research at LMMP in PUC-Rio, where Sérgio Ribeiro, Frederico Gomes, Márcio Carvalho and I developed a preliminary method for equivalent permeability prediction of Karst core samples using deep learning. Digital rock analysis plays an important role to estimate average properties of rocks for oil and gas industry, such as porosity, surface area, and pore network extraction. Micro-CT image is also used as the main input for modeling fluid flow at the pore scale to estimate flow properties from a numerical simulation, such as permeability. Pore network model uses a simplified geometry representation of the pore space, using pores and throats. It can compute larger domains. However, it does not represent the actual geometry. Direct numerical simulation deals with the real pore structure, but it is complex and more expensive. The motivation for this research relies on carbonate reservoir, which presents pore space at different scales. The presence of fractures, vugs, and caves, interconnected or isolated, significantly affects the flow characteristics, especially connected vug pore systems that dominate fluid flow. This image is a slice of a coquina sample. The black areas are the larger cavities, the macropores, and the grayscale, the porous matrix with microporosity. So, solving flow in void space at multiple levels is a challenge due to the complexity in vug geometry and the presence of micro and macropores. The question is, how can we compute the permeability of a carbonate? Conventionally, on the microscale, porous medium flow is described by the incompressible Stokes equation. However, it leads to a problem of geometric scale, with thin channels of micrometer and a large void of centimeter size, what makes the solution extremely expensive in terms of computational cost. Alternatively, on core scale perspective, the flow can be described by Brinkman equation that gives a simpler transition between Stokes and Darcy equations. Here, there are two domains, the Darcy domain with a given permeability value for the porous matrix, and the Vug domain, the free flow region ruled by Stokes. With a single equation to describe both domains, we avoid the imposition of a boundary condition at the interface among domains. No matter which option you choose, solve the flow problem numerically is not an easy task. Thus, is there a way to compute equivalent permeability without numerical simulation? The objective of this work is to train a deep learning model for fast prediction of the increase in permeability caused by the presence of vugs. As I said, performing direct simulation is complex and the whole process takes much time. On the other hand, convolutional neural networks requires a huge dataset. With more data, better the model, higher will be their accuracy. Here, we combine the CNN-based image only with direct simulation of two slices of a core sample to build the training dataset and after predict permeability for new image faster and less complex than direct simulation. Our method to reach this goal is to develop a workflow to train a convolutional neural network to predict equivalent permeability. To do it, we first acquire CT images of a carbonate sample. Next, we segment the image, create meshes, and implement a numerical model to solve flow in two-dimensional slices. After post-processing step, the equivalent permeability is computed. The binary image computed permeability pair will constitute our database. With these values in hand, we train a convolutional neural network using those binary images to instantly predict equivalent permeability for unseen images. We selected the coquina core sample, which is composed by the accumulation of shells. After scanning the core sample, the dataset images were segmented using automatic threshold to distinguish porous matrix and vugs. The vug is formed by the dissolution of shell parts and mud. Here we consider the black regions an empty space, the VUG area. White means a porous matrix region. We also create from each CT slice processed 3 new artificial images using different intensity thresholds. As a result, images with even larger VUGs were constructed. For the direct numerical simulation, the contours of the VUGs were extracted from the binary image and after discretized in an unstructured mesh. The unstructured mesh contains the Darcy domain, porous matrix region, and VUG domain, the Stokes area. The finite element method was applied in order to find an approximate solution for the governing equations. In this case, the system composed by Brinkman equation and mass conservation. The given permeability used for the porous matrix is 1 millidarcy. Around 6,000 images were processed. The simulation tool solved single-phase flow through those geometries on X and Y direction, resulting in around 12,000 outputs. With each velocity field from the numerical solution, the average density velocity was calculated, and the equivalent permeability back calculated. After, this value is normalized by the porous matrix permeability value. On this graph, the normalized data is plotted as a function of the VUG area of each processed image. We arrange data into 2 groups. The blue points have lower equivalent permeability variation due to a lower range of macroporosity. Then we performed a preliminary test with group A, which has lower variability. 5,686 binary images are chosen for training, and 632 images were preserved for testing the network model. Most images are between 0 and 10% of VUG area. For the second test, we used the coquina core sample entirely and the artificially generated image. There are around 12,000 data values and above 1,000 reserved for testing. Group B adds to the model images between 10 and 30%. We adopt a neural network with convolutional layers that have proven very effective for image pattern recognition. The supervised learning approach applied used the binary image and the normalized computed permeability as input-output pair. For example, this image is an original image taken from the coquina sample that is without VUG enlargement. It presents 506 VUGs corresponding to almost 10% of VUG area. The computed normalized permeability in X direction is 1.20. So, these VUGs increased the permeability in 20%. In this figure, we can see the details of the relevant parameters of the convolutional neural network architecture. We implemented the network model in TensorFlow, using just the binary image and the normalized permeability from the numerical model as a target. The convolutional neural network model was trained to minimize the error between predictions and the expected value, using mean square error as the loss function. The computational wall time for training is around 4 hours. The test answer is in milliseconds. The results for test A showed high accuracy, above 98%, an excellent estimation. On this graph, CNN results are plotted against the numerical predictions. In this case, the best value for R-squared would be 1. This measures the strength of the relationship between CNN predictions and the actual value. The measured R-squared was 0.83. Most of the permeability values randomly selected for testing are concentrated between 1 and 1.2. The deviation was higher for the highest normalized permeability values. On residuals graph, we can see better how close the CNN predictions are to the target. Just 1 point, the highest permeability point, is slightly far from the computed normalized permeability. that is the x-axis. The average relative deviation is 1.73%. For test B, with wider variability rate, the accuracy was higher than expected, but lower than 10%. The model accuracy is 90.66%. The linear regression value is 0.88. Checking the histogram plot over here, permeability values are more spread out. Once again, the deviation is worse for high permeability values, where there are fewer data to train the convolutional neural network. This network configuration reads 9.34% of average relative deviation for the most geometrically complex testing samples. Another Karst sample was submitted to the CNN training. The network construction followed the learning of case A. Almost 3,000 values based on original slice of the sample, image segmentation only, are chosen for training, and around 300 preserved for testing the network model. Most images are between 10 and 20% of VGR. Although both samples were extracted from the same formation, they are very different. We can see in these pictures without VUG manipulation that the second sample contains larger VUGs. The macroporosity average for the second sample is 12%. For the second core, the prediction accuracy is 95.3%. The measured R-squared was 76%. Most of the permeability values for testing are concentrated between 1 and 2.5. The deviation was higher for the normalized permeability values, far from the concentration of data. Once again, the deviation is worse for the highest permeability values. Within the range of highest data frequency, the residual was low. The average prediction deviation is 4.7%. Summing up, in both cases, the accuracy of the CNN was lower for the highest normalized permeability values, probably due to there are fewer slices above 20% of macroporosity, difficulting the network training. For the original image extracted from the cocaine sample, until 90% of VGR for the first core, this method using just a binary image as entry to predict normalized permeability was effective. This was the case of group A and the second core. Case B showed the limitation of this convolutional neural network architecture. The overall error is acceptable, but a data segmentation before training is required to avoid unbalanced representativeness. Similar to case A, the prediction for the second core with higher macroporosity showed good accuracy for the segmented CT slice without VUG enlargement. For future work, the plan is to incorporate physical features such as macroporosity, surface area, and average VUG length to enhance CNN prediction. Another important issue is to make predictions based on grayscale image, not just binary image, for triple porosity media such as Karst reservoir. Finally, I would like to thank all the financial angels that supported this work, and thank you for your attention.